Hello, everybody. Thank you for coming back. We have 117 people listening to our presentations. We are in the coronavirus mode, but when I talk to you and to the camera, I can take off my mask and always have a reserve mask here ready if the problem arises with the pandemic. I have the pleasure now to salute and introduce Hirooki Tokoi from Hitachi. He has a PhD from the Tokoi University of Japan. He will talk about efficient motor technology with low-loss soft magnetic material. This is really for the motor cracks who are interested in how material technology can be improved to gain more efficiency and better motor. Hirooki has been involved in research on permanent magnet motors and appliances. Welcome, Hirooki. You have the floor.
Hello, I'm Hirooki Tokoi in Research and Development Group of Hitachi Limited. Today, I'd like to talk about efficient motor technology with low-loss soft magnetic material. I'll make a presentation along the following these contents. First of all, I'll give introduction of Amorphous motor of starting point for this development. Then I'll talk about study for further high efficiency and development to radial gap type motor. Finally, I will finish today's presentation with short conclusion. At first, I'd like to explain introduction of Amorphous motor. This graph shows a trend of the world's electric power consumption. And the electric power consumption goes on increasing year and year. And this pie chart shows electric power consumption for each application. 40% of the total electricity is consumed in motor applications. Therefore, high-efficiency motors are required to decrease the electric power consumption. In this situation, we are developing high-efficiency motors using low-loss soft magnetic materials. This slide shows magnetic characteristics of soft magnetic materials. The horizontal axis is iron loss and the vertical axis is magnetic flux density. Amorphous metal has a very small iron loss compared to electric steel sheet. Therefore, we decided to use the amorphous metal for a motor. Moreover, high BS nanocrystal is an ideal material for motors that satisfies low loss and high magnetic flux density. This application will be introduced in the next chapter. The biggest issue when using amorphous metal in motors was the processing. Amorphous is very thin and hard material, as shown in this table. So, as shown on the right, processing and deterioration of magnetic characteristics and so on became issues. Therefore, we thought we need a new iron core structure for amorphous metal that can be easily processed. This slide shows the method of cutting and laminating amorphous metal that we have established. This figure shows the manufacturing image. In this method, an amorphous metal can be made into an iron core only by sharing. Therefore, the core can be manufactured very easily. In this situation, we developed technologies to build a high-efficiency motor. As shown in this figure, this motor has axial gap structure and amorphous metal. And this graph shows motor efficiency. The prototype of 11 kilowatt amorphous motor in 2014 achieved an efficiency of 96.2%, which satisfies I5 standards class. In addition, it was thinner than a conventional induction motor. By taking advantage of these features, we have commercialized a scroll compressor in 2017. In conventional compressor, I3 induction motor and compressor are connected by a drive belt. Therefore, we had developed new compressor with integrated amorphous motor. The integration was realized by significant shortening the motor shaft and cutting motor losses. Developed compressor has roughly the same dimensions as the conventional induction motor. As a result, the package size had reduced to 37% of the previous model. Next, I will talk about study for further high efficiency. In this study, we aimed for development of further high efficiency motor. This pie chart shows the loss composition of the i5 11 kW amorphous motor in 2014. Motor loss occurs in coils, bearings, cords, housings, and so on. To further increase efficiency, it is necessary to reduce the loss of coil and housing. Next, let me explain about these loss reduction measures. This slide shows countermeasures policy and concrete means for loss reduction. A. To reduce DC copper loss, we reduce current by increasing magnetic flux. Concretely, we applied high BS nanocrystal and high BR bond magnet. B. To reduce AC copper loss, we reduce electric resistance. Concretely, we applied multiple fine wires. C. To reduce housing loss, we reduce eddy current by increasing electric resistance of housing. Concretely, we applied non-magnetic and non-conductive ceramic housing. This slide shows design changes about magnetic core and coil. Combination of bond magnet and nanocrystal increase the magnetic flux. It leads reduction of input current and number of coil turns or winding resistance. In order to reduce the AC copper loss, we reduced the wire diameter. Next, I will explain countermeasures for housing loss. This figure shows distribution of eddy current density. Eddy current is caused at housing by leakage flux from coils and magnets. Since it is difficult to make the leakage flux zero, we focused on housing material. This graph shows the relationship between resistivity and strength of various housing materials. It is clear that ceramic is an excellent material for both properties. This figure shows cross-section of 11 kW nanocrystal motor. The motor equips high BS nanocrystal, high BR bond magnet, ceramic housing, and high thermal conductivity resin. The test motor is the same size as the i5 11 kW amorphous motor in 2014. This picture shows the prototype of 11 kW nanocrystal motor. This is a stator core made by laminating high BS nanocrystal. The stator is made by integrated cores coils and ceramic housing with aging. This is a bond magnet rotor, and this is an appearance of prototype motor. This bar chart shows the motor loss at rated output compared with the Amorphous motor. This table shows the loss reduction measures applied to non-crystal motor. Total loss is reduced by 40%, mainly in coils and housing, and motor efficiency achieved 98.3%. In this section, I'd like to explain deployment to radial gap type motor. This figure shows the radial gap type stator structure using amorphous metal. Amorphous is applied to the stator teeth. We thought that this simple trapezoidal shape could be made by sharing and laminating method. The amorphous teeth core is assembled by inserting into the yoke. The yoke is made of divided electromagnetic steel sheets to improve the utilization of punching. This radial gap type motor is expected to be applied to applications that require operation in higher rotation speed and harsher environment. This slide shows the target specifications of the prototype motor. The figure on the left shows the cross-section structure of the motor. The outer diameter is 215 millimeter. The number of rotor poles is 16, and the number of stator poles is 24. This is concentrated winding motor structure. The target motor capacity was set to 11 kW, the same as the i5 axial gap motor. This slide shows the stator iron loss when changing the material of teeth. In case of using electromagnetic steel sheet, there is a loss of 110 Watt on the teeth shown in the left figure. On the other hand, in case of using amorphous metal teeth, loss is reduced to 26 Watt. By applying amorphous, the stator iron loss is reduced to 1/3. This is a cross-section view and an external photograph of the prototype motor. The bearings and shaft are from mass-produced industrial 11 kW machine. Motor volume achieved the target specification. This slide shows the parts of the prototype motor. The yoke core made of electromagnetic steel sheets. This is made by wire cutting. The amorphous teeth is made by wire cutting too. The teeth is held by a resin bobbin and a coil. The rotor is a surface magnetic type, and FRP was wound on the outside. This slide shows the efficiency of the prototype motor. This graph shows motor efficiency, and the motor efficiency is 97.2% at rated torque. This table shows the comparison with the axial gap machine and radial gap machine. Since the magnetic materials are different, simple comparison is not possible. but both have achieved higher efficiency than i5. In the future, we would like to consider further speeding up by taking advantage of features of the radial gap structure. Finally, I will make a conclusion for this presentation. In this presentation, we explain the technology for further improving the efficiency of amorphous motor and the technology for expanding the application. High efficiency technology. We propose new axial gap type motor with high BS nanocrystal core and ceramic housing to reduce kappa loss and housing loss, which dominate in axial gap type amorphous motor. The motor efficiency was improved from 96% to 98%. Expanded application technology. We propose radial type amorphous motor consisting of amorphous teeth and electric steel sheet core back. The amorphous teeth can be manufactured with relatively simple processing. And the prototype motor achieved an efficiency of 97%. Thank you.
Thank you very much, Tokoi-san. Konbanwa. Konbanwa. Can you hear me? We don't hear you.
Hello.
Now we hear you. Okay. Thank you for your excellent presentation. I'm glad to hear that efficient motors can still become more efficient, more efficient, more efficient. The first question we received is, when can we buy such a motor on the market?
We on 2017 we have sold the scroll compressor with amorphous motor.
That means the compressor with the amorphous motor was already
Yes.
on the market
Yes.
2017.
Yes.
And any other products are available? Can I order from Hitachi now a amorphous motor? Yes?
Yes. Yes.
Only small size, 10 kilowatt, or also large size?
7.5 kilowatt.
Only?
From 3.5 kilowatt to 7.5 kilowatt.
From 3.5 like this to 7.5 like this?
Yes.
And our question, are these motors more expensive than normal induction IE3, IE4?
As you say, the amorphous motor is higher than conventional motor, but the material cost is not higher than conventional one. The reason of higher cost is manufacturing cost.
Yeah. One question is, can we see this amorphous motor also for automobiles, for cars?
Yes. We want to apply amorphous motor to automobile. So we are developing a radial gap type amorphous motor.
And can you go up to high speed? Now we can go to 6,000 RPM or more? Rotating speed?
Yeah. about 10,000
How much? Say again?
RPM.
10,000.
10,000
Ichiman.
RPM.
はい。
Yes.
Okay, わかりました。And let me see the other questions. I understand, and you just mentioned, that the material costs are about the same. The manufacturing cost is higher. We
Yes.
know that cutting amorphous steel is very difficult. What is the new invention Hitachi made to cut amorphous steel? Wakarimasen?
Yes.
Okay, you didn't understand my question. Okay, then I go to an easier question. You mentioned the motor can also be smaller. Yes?
Yes. Yes.
Hey, what kind of application do you have in mind? You talk about compressor.
Yes.
And what else? Pump?
Automobile.
Automobile? Pump?
Pump.
Fan?
Yes.
Everything. Okay. Next
Okay.
year.
Yeah. Axial gap type amorphous motor, we can apply immediately
Okay.
various product.
Okay.
But radial gap type is on study.
Okay. Thank you. Arigatou gozaimasu. Very interesting presentation. We wish you all the best for the future development of amorphous motors. Thank you.
Thank you.